Okay, so in today's lecture, we are going to continue our classification module. So today we're going to talk about a new model called naive Bayes classifier. So as you can see, this is a classifier, means we are working with classification problem. So this is short for NBC, naive Bayes classifier. And let's start with the setup. So setup, we have a training data, D. As xi is a feature, yi is the label, I from 1 to the n. This y here can be either binary or multi-class. It doesn't necessary to be binary. It can be a multi-class as well. Okay, so the assumption in naive Bayes is following. Is those features are conditional independent. Independent, given the class labels. So that means if you have a probability of my x conditional on y equal to certain label c, and with certain parameter theta, then this is equal to, you actually, it's conditional independent. So that means the probability I can multiply them together for each component. So that means it's multiplication of little d from 1 to big D. Say my x right here is in big D, of probability of xd, which is each component conditional on y equal to c, and the theta right here. And the theta here is only depends on d and c right here. So I have a theta dc here. So this is actually theta dc, a parameter for the class conditional densities for class of C and feature D. So you can see this assumption here. So that's the only assumption that we have. This assumption that we have is very naive. It's usually not true in reality. We don't expect those features to be conditionally independent on class label. So this is a very naive assumptions. Although we don't expect that in reality, but turns out these assumptions our model can still perform well and very well with under such naive and simple assumptions. So the second thing is this model is very simple. So we have naive, and we also have a simple here. Because the model is very simple, and we only have to work with C and a C class, and we have a D features. So here we assume we have C class and a D features. So that means we have parameter of theta dc. So in total, this theta right here is we have C times of D parameters. So this is quite small compared to other parameters that we're working with. We only have C class and D features. If you think about the other methods, and we're going to talk about this later on, called QDA. It's called quadratic and discriminative analysis. They have significantly more and the parameters in the cases. So if we only have C times D parameters, it's, I mean, it's likely will not overfit. So the key is may not overfit. Since we have so few amount of parameters to work with. All right. And also this is, has a like much broader application here, because here we don't assume and what kind, so let me just say, this is order of C times D, because sometimes it's not precisely C times D here. It might be either 2C times D and so on. And also we can build more models for this conditional probability P here. And this conditional probability P can be Gaussian, can be uniform, can be whatever, and the distributions that you have depends on the models you want to work with. Okay, so then with this conditional probability, the key is what is the posterior distributions over the class labels. The posterior distributions over the class label is the following. So that means it's probability y equal to C, conditional on x and theta. So this is the posterior distributions. By definition, this is equal to y equal to C, conditional on conditional, that's the prior. So wait, let me think about this. Yes, the prior. So this is the prior here. So let's just have some prior. It's also has parameterized by pi. Then we have probability x conditional on y equal to C and theta here. And a summation on C prime for all C's here. And pi y equal to C prime and theta. And of course, that's my conditional probability. We can use the factor that we already talked about. This is multiplication of little d from 1 to big D, probability x of D, conditional on y equal to C, d theta dc, divided by summation C prime. The same thing, just we plug in so a thing that we just calculated. Conditional on y equal to C prime and theta dc prime. So this C prime is you actually have to go through all possible C's. And of course, my theta here is the parameter. In this case, we have two set of, we have a prior, which is pi, and then we have a theta, total. This is, and it depends on the D and the C. So this D and C is from 1 to the D, and C is from 1 to the C. Okay. So this is basically my posterior distributions. And also, if we can find out this posterior distributions, then we can easily make these predictions. So the prediction is the maximum label such that this posterior probability is maximized. So this make a prediction for the new data is C of argue max of the C prime of probability of the posterior distributions. Right, so basically it's very straightforward. All you need to do is calculate this posterior distribution for all possible C, then find out the corresponding like labels such that to maximize this posterior probabilities component. So let's show some particular examples of the models particularly. So for example, we can think about the binary cases. So in these cases, this XD right here, it's either 0 or 1s. So the feature that here we can only get is 0 and 1s. So and what does that mean is we have some like multivariate and the Bernoulli naive Bayesians. So that becomes multivariate naive and a multivariate Bernoulli, sorry, and a multivariate Bernoulli naive Bayes. So what does that actually mean? And you have a whole bunch of features from x1 to xd, and like each component can only be 0 and 1. So that would be multivariate Bernoulli and a naive Bayes right here. Total the distribution that we got is x given y equal to c, and the theta here. So as I said, that would be the multiplications of this Bernoulli distributions of the x of d conditional on theta dc. Right, so here, and we can give like a precise like definition of theta dc. Theta dc is equal to probability the xd equal to 1, conditional on y equal to c. That 1 minus theta dc is probability xd equal to 0, conditional y equal to c. Okay, so you can think about this Bernoulli. Distributions can be written as has the following and an expression that is we multiply 1 to the d of x of theta dc of power of x of d, then multiply 1 minus theta dc of 1 minus xd. Right, so this tells you if you like using this way right here, and if xd is equal to 1, this will only give you theta dc because everything here just being 1. If xd is equal to 0, then this term is gone. Then we only have this is 1. It left with 1 minus theta dc. All right, so this is the binary, so multivariate Bernoulli naive Bayes, which each feature can only be chosen as 0 or 1s. So the second things that we can do is categorical features. So categorical features. So that means this xd is not in 0 to 1, but actually 1 to k. So this is, as a result, becomes multivariate. Categorical. Naive Bayes. All right. So in terms of distribution, this becomes probability of x given y equal to c and the theta here. This becomes multiplication for each component d from 1 to the big D, categorical of x of d given theta dc. Dc. And this theta dc becomes a vector, which it's actually theta dc k is equal to probability of xd equal to k conditional on y equal to c. So this is actually the and the multivariate categorical naive base, and also the summation of theta dck is equal to 1 if you sum all possible k's. So this is the situation if you want to work with MNIST data set. That's the categorical features and you should and work with. And because in the MNIST data set, this values is actually and from 1 to 255 and all like and pixel values. So that's you can think about as a like multivariate and a categorical and naive base. Okay. All right. So the third one is if we can third one if we can think about is real value feature. So this x of d is actually in the R. So and what we actually to build a model is probability x given y equal to c and theta is actually a normal distributions usually as some mu mu as a function of c and some like diagonal and variances. So it's sigma c of identity right here. So mu is also a vector here. So this is basically it's kind of like an Gaussian discriminative analysis. And we're going to talk about this a little bit in detail later, but when we talk about an Gaussian mixture model stuff. But this is just give you some heads up. But this is the Gaussian discriminative analysis with a diagonal and variances. The reason that we have this diagonal variances is just because if we and imposing the 4 variances, this is usually have a big issue here. So we have something called an overfittings. And we're going to talk about this again, in detail of the later of the courses when we talk about corresponding and GDAs. But this I'm just saying, this is a diagonal. So like, precisely, so this will be, and we also need to multiply them and together. Wait. So this is, I have, I'm pretty much wrong here. I think I have a D here, x of D. Yeah, so this will be just mu CD, mu DC, and sigma DC square. Basically, each component, I mean that will be a Gaussian. But if we like vectorize the, x here, if we think about the probability of x conditional on y equal to c and theta, this is basically an Gaussian distributions with the variances on the diagonals. But this is also equal, and we need to multiply them together, right? So this is equal to, and the multiplication of d from 1 to the big D of this Gaussian distributions of, this is, I forgot xd here. xd given of mu dc and sigma dc square, and we multiply them together. Then mu dc, is the mean for the feature of D when the class label is C, and then sigma dc square is the variances and the corresponding variances. So these are all the models, but I think we were just focusing on this ones, on the categorials and specifically for this lectures. Later on, we're going to talk about this QDA in detail, but for now, let's just focus on the number 1 and number 2. Okay. So we talk about prediction here, and we haven't talked about model training or model fitting here. So the way to do the model training is very straightforward. We need to find a way to minimize the negative log likelihood. Then we can find out the optimal theta in these situations. All right, so this is basically the first thing is we need to find out the MLE in this cases. The MLE in this case is probability D, conditional on theta. By definitions, so like model training is, I like to say it's maximize log likelihood. So we want to find out MLE here. It's multiplication of I from 1 to the n, since this is an ID sample. Then we have the categorical data of yi, conditional on pi. This is your initial distributions. Sorry, and the prior distributions. Then multiply little d from 1 to big D of probability of xd of I, conditional on yi, theta d. All right, so this is basically the likelihood functions. We can rewrite things a little bit to include the C, right? Because here we assume this is equal to yi equal to C here. So we can, so include these things. And this whole, expression can be written as multiplication from 1 to the n, same thing. Prior is the same. The next multiplication here can be written as multiplication of D from 1 to the big D, multiplication from and the little c to the big C. Then probability of xi as xd to the I of theta dc, power of 1 indication function of yi equal to C. Okay, so that means if it is yi equal to C, that would be 1. I'm going to pick this probability. Otherwise, I'm going to mute the other component. Okay, so of course we are taking the logarithm for this likelihood. So this is likelihood. We're going to take the logarithm of likelihood. If we take the logarithm of this likelihood, this is summation I from 1 to the n of, if we summarize all possible cases from 1 to the c, capital C, this becomes C from 1 to the C. So this is, and this part is nothing but we're trying to fit a multivariate and the categorical distributions. So this is one of yi equal to C, like indication y equal to C and the log of pi, pi C. Okay. Then plus summation I from 1 to the n, summation C from 1 to the C of, sorry, D. Wait, that's not right. The D, yeah, yes, C the, yeah, okay. Multiplications of, wait, is it wrong? Just a second. Yes, I think, I mean, my notes there is, something is missing, which I missed the summation of I here. I forgot. This should be summation of I from 1 to n, C from 1 to C, and a D from 1 to D. And the next is going to, oh, yeah. Yes. Yes, that's right. I'm sorry, I was wrong. I'm right. So I need to sum about the corresponding of I, that yi. So basically I re-summarize and rearrange these summations into C different categories. I'm going to pile every yi equal to C into one pile. Then I'm going to calculate this corresponding summations. I'm going to calculate each component, each parameter separately for different C's. So this becomes logarithm of P of XD of I conditional on theta DC right here. So basically this is implicitly being included from and to some I from 1 to the n, but we are piled into C different groups. So this is, I mean, very important here, so that we don't need to worry about this indication function, because, and within this and group, and that indication function is already like automatically satisfied. Okay. So, and I want to remind you how many parameters we need to infer. We have to infer the pi C right here. We also need to infer the theta DC. So my whole parameter here is my pi C and the theta DC. And D is from 1 to the D. C is from 1 to the C. Okay, so if we merge everything together, so we can just write something a little bit more compact. We can write everything into logarithm of probability of dy conditional on pi plus summation of C, summation of D of log of probability of D dc conditional on theta dc. So that means I'm going to separate the data into those groups. The first dy here is all of my data yi from 1 and I from 1 to the n. So I'm group this, and these are all the labels. The data of DC here, I'm interested in all my feature of xd of I that my yi is equal to c. So I'm interested in my corresponding feature xd and also my yi is equal to c. All the values of feature d for the examples from classes. Okay, so you can just write everything basically separately because we assume conditional on y equal to c. All these features right here is independent, so that we can consider completely separately. Okay, so for pi, MLE for pi, this is the same as we trying to calculate MLE for the categorical distribution. So this is just simply the empirical count. So this pi c hat is nothing but NC divided by n. So basically just the empirical count of all the labels. And MLE for theta DC, it actually depends on the class conditional densities that you choose. If we choose the categorical, so it depends on the choice that we make for the probability of x y equal to c and theta. So like depends on the model that you choose. In the categorical, the MLE says the theta dck hat, it's nothing but, everything separate. We can just calculate the number of the counts that for the feature of D, and my label is C, and the K has the value of K. The feature has the value of K divided by summation all possible K value 1 to the capital K of N D C K prime. All right. So right here, so this NDC K is basically with all the numbers times from 1 to the n of indication function that my xd I equal to K and my yi equal to C. So you basically sum all possible. So you basically sum, if you sum with all possible value K from 1 to the K, so you sum up with this index of xd. So it actually ends with has NC numbers and NDC. It's ND, so DCK here. Because it basically marginalizes the variable xdi equal to k. So if we sum of k prime from 1 to the k of n dck, this is summation of k prime equal to 1 k indication function I from 1 to the n, indication function xd I equal to k prime, and the yi equal to c. Right, so if we sum them together, it becomes the indication functions sum of I from 1 to the n of indication functions of yi equal to c. Right, so this becomes nc. So this is a bit, slightly trickier, but that's how that we have here. So if we have a Bernoulli instead, that means we have, instead of categorials c bigger than 2, we only have a situation with the 0 and the 1s. With the Bernoulli or binary and features, then this categorical distribution becomes Bernoulli. Then this theta dc hat, which is only the probability that this features is equal to 1, because we know if it's like 0, that will be 1 minus of probability of that feature to be 1. This will be n dc, so we don't have a k values anymore, divided by nc, which is the empirical fractions of like feature d on so examples of the class of C. Right, so this becomes my C becomes 2 in this cases. So sorry. If we have binary features, it becomes a Bernoulli distributions. And of course, that's MLE. Okay, so categorical, we have like Bernoulli here, and also we have a like real value, we have a Gaussians. Right, so that means it's corresponding to the real value feature. So here I'm not going to go and derive this, because you're going to derive this anyway later of the courses. This is mu dc hat, and it's 1 over n, and which is basically empirical mean conditional on yi equal to c, xd of I, and the sigma dc squared. It's 1 over here is nc, right? 1 over nc, and which is empirical variances. So this whole argument and the derivation is very similar to the Gaussian mixture models, and you will see these things again when we talk about QDAs. So this is empirical mean. So this is also empirical variances. All right, so you can see this is quite simple and efficient. All we need to do is just to do some countings. And once we do some countings, we just, calculate, either categorical probabilities, multivariate, distributions or Bernoulli distributions. So which corresponding to this theta hat dck, or we have a theta dc if it is binary. If it is Gaussian, that will be just mean and the variances. So all we need to do is just to do some simple counting. That will give us the fractions of probabilities that we'll be interested in. So once we know those and these probabilities, which is conditional probabilities, at precise values, then we can use it to make predictions for the new data coming in. So all we need to do is to calculate these posterior distributions, then find the argmax of this posterior distributions, find the corresponding labels to maximize these posterior distributions. This will be our predicted labels. All right, in the next part, we're going to talk about some examples and also connections with logistic regressions.